Got it.
Then the next kind of effects, again, systematic effects, is proximity. If there are devices which are placed far apart, there is more spacing between devices versus devices which are placed close together, you will see that the kind of stress that appears in the diffusion region, in the region where you have your contacts and everything present there, it changes. Look at the contours in the bottom graphs. The stress changes, due to which the PMOSes and NMOSes start to behave differently. In fact, it was said that 28 there is the P by N ratio changes by 28%. The mobility of the NMOS and the PMOS, the ratio changes by 28%. That huge an impact can happen.
So which stress are you talking about here, sir?
Stress. Okay. So let us say this is a device. There will be shallow trench implants over here on the side. So as soon as these shallow trench implants come into picture, what happens? The crystal lattice, the crystal lattice is broken. When the crystal lattice breaks, there are bonds which are dangling. There are bonds which now see a different kind of stress. That stress gets, as you can see in the contours, that stress gets transmitted to the gate region also. Are you able to see this?
So I mean, shallow trench implant able to get, but what is causing stress actually?
The breaking of the bonds, the breaking of the lattice structure of the silicon.
So due to the STI, shallow trench implant.
Yeah.
So the process
otherwise this was all silicon. Otherwise this was meant to be all silicon. This was meant to be complete lattice of silicon. Is it not? You broke it with STI here and there. Due to which devices now have stress. And the stress is different when there is a sparse device, sparsely placed devices, and it is very different when they are densely placed devices. Because STI can absorb some part of mechanical stress. It will not absorb all the mechanical stress. Or when there is a lot of STI, it gives a different kind of stress versus when there is a little bit of STI there. Okay.
So sir, like when we have the dense layout, so I can think of ki STI, the width will be less. I mean, the shallow trench will be smaller. So that will lead to different kind of stress. I mean, the physical. Okay.
Yeah. So you design the layout, तो आपको दिखेगा ना कि यहाँ पे STI कम है कि ज़्यादा है ना? And look at this. This is the result of the final simulation in terms of ring oscillator. The dense ring oscillator operates at a higher frequency than the sparse one. Overall, we saw that there is more than 10% timing variations just because of this effect.
So it means that stress is changing the device characteristics itself. I mean.
Yes, mobility changes, na? If there is stress in the silicon lattice, the way the electrons will move around will change. When you are under stress, does your performance change?
Yes, sir.
Exactly the same way, the transistor performance also changes. Ranjit?
Sir, what exactly is this STI, sir? I'm unable to understand this.
Shallow trench implant. We discussed about shallow trench implant in the second lecture of DVD, manufacturing process. How do you separate two devices from one another? You remember we said we would break open we will make shallow trenches between two devices and we would deposit. So before shallow trench implant technology, we would grow silicon dioxide on silicon itself. that led to that beaking effect. Remember? Between two devices, there would be a beak that would form, and there was a minimum DRC that was supposed to be maintained. We said, okay, we do not want to go with this beaking etc. wala funda. We will open up. We will open up the silicon and deposit oxide in there, so that we can have denser layouts. We will not depend on growth, because that would mean beaking would happen. That would mean more spacing between devices. So for density, we went for shallow trench implants, where the silicon is broken open between two active regions. We deposit silicon dioxide.
Okay, sir.
Okay. So that is the impact of device variation. So see, at that point of time, some of you might have felt why we are discussing all this manufacturing steps. It is very important, because as a designer, you need to understand what all effects those manufacturing steps could have on your design. Okay. So similarly, we already discussed the dishing in wires. You remember that? The dishing phenomena in wires, because when we do chemomechanical planarization.
Yes, sir.
So how do we avoid this?
Sir,
Adding some
SiO2 in between.
We add some pillars of SiO2 in between, so that the dishing doesn't happen. We make some slots inside wide wires. Ranjit?
Sorry, sir, I forgot. No.
Okay. So we add slots inside these wires, so that those slots act as pillars and dishing doesn't happen. So this is again one of the systematic variations. You see a wide wire, you know that, okay, there is going to be some loss. You see sparse density of wire, you say, okay, there is expected to be some loss. So why is it important in terms of memories? Where do you have wires running around?
Array.
In the memory array, there are word lines, there are bit lines. So there is a huge density of wires. If suppose I say that I want to track my word line capacitance with a word line capacitance and resistance with a signal in the IO region, is there such a requirement? Is there a requirement to match word line with some signals in the IO?
No, sir.
No? Why?
So can you repeat the question?
Is there a requirement to match the RC of word line with some other signals in the IO region?
Yes, sir. I think if
recharge.
Yeah, we talked about the race conditions in the IO. That was the last slide we discussed. We saw that in the IO, the precharge should come before word line. We saw about this condition, the race condition. What does this mean? That the RC of precharge signal should be similar to that of, or at least there has to be some semblance of some relationship, deterministic relationship between RC of word line and RC of the precharge signal. So if, for example, now you in the IO region, you make precharge line as a single line running, with 1 micron distance spacing to any other line, will it behave the same as word line? Will it behave the same as word line? Hello?
Sir, the precharge line, in the sense you mean like the clock that is going to the precharge circuit in the sense.
The metal that you route, route to connect the gates. Finally, you will route metals, na?
Yes, yes.
So that metal is very sparsely placed. There is no other metal wire within 1 micron of it. That versus the word lines in the array region. Will you say that these two lines are matched?
So I mean, I'm looking at the how the wires are placed, the surrounding of the wires basically.
Yes.
So, but okay.
And the word lines
Density.
are spaced.
Because if the wires are dense, if the wires are densely placed, there will be lesser dishing. If the wires are sparsely placed, there will be more dishing. Or vice versa. Basically, softness of copper is different from the softness of silicon dioxide. So if there are more wires, it means there is more copper in that region. The CMP process will polish it in one particular way. If there are lesser wires, it means there is a different level of hardness in that region. The CMP process will polish it in a different way. And your wires and delays may not be matched. You wanted to match the delays, na? But the wires have different RC now. The delays are not matched.
So just because the different surroundings,
Yes.
we can have different
Yes.
RCs.
You see, that is the and this is a systematic variation. This is what we mean by structural matching. That the structure of the layout in terms of density and everything should be matched. The bends that you see in the for one device should be similarly made for the second device also. Everything. Ranjit?
Sir, if the wires are placed denser to each other, then the chemomechanical process cannot polish out, the dishing cannot happen for the densely placed wires.
Yes.
But
So those wires will have lesser resistance.
So
Yes.
what does dishing mean, sir? I'm not.
So dishing means that CMP, during the CMP process, as you see in this right side figure there, when there are wide wires, they end up eroding, eating away the copper more than what was desired. Because copper is much softer than silicon dioxide.
So
So
the
CMP
dishing,
process polishes it more.
so sir, it happens when the wire is not dense.
When the wire is, what do you say? When there is a lot of wire, lot of copper, because copper is soft, dishing will happen.
Sir,
Okay.
where did density come into picture, sir? Exactly. I didn't, because the according to what I understand is that it depends. It totally depends on the width, right? Why
Dishing
are we
depends on the
talking
width, but we are talking about another effect, erosion over here, or field loss over here. See, look at the slides. There are two new terms which have been introduced, field loss and erosion.
Okay, sir.
So when there are so many wires, overall softness of that region is lesser than places where there are no wires. So more erosion will happen.
Sir, but suppose if we consider the case of denser wires, sir, the dishing will be less, but the intrametal capacitance will increase now, sir. So that
Yes.
time RC also increases.
We don't know. Resistance is lesser. Because the wires are taller, the resistance is lesser now.
But C capacitance increases.
Yeah, C may increase. Now, do you realize that if R and C values move differently, they are moving differently now, is it not?
Yes, sir.
R reduced by 20%, C increased by 10%.
Yes.
RC would move in a different direction.
Yes.
Anything, whatever it is, the two wires, word line and pre-charge line, are not matched if they do not have similar density of wires around them.
Yes. Yes, sir. Absolutely.
That is the point that needs to be established. Okay. Raghav?
So what do you mean by the field loss here, sir?
The field oxide, SiO2 loss. When you do CMP, the field oxide will also get polished, na? Okay.
And what is erosion, sir? Here.
Erosion means in between the wires. So field loss is in those regions where there is not much density. So you see, and that is exactly what I was mentioning about. You know, when there is not much wire density, the height would reduce by only this much. But where the wires are denser, the height would reduce by a larger amount, and therefore your wires will be thinner, less tall.
Okay.
Okay. So that was where we talked about metal slotting earlier. And now today I'm introducing this term, which is called as dummy fills to you. Okay. So dummy fills are also done so that you have similar level of density at all places. However, inside the memory, you do not allow any dummy fills. Inside the memory, you want as a designer everything to be under your control, is it not? As a designer, you want the memory to behave exactly the way you want it. Right? So inside the memory, dummy fills are not allowed. But outside the memory, that is in the standard cell logic region, dummy fills are done so that dishing and erosion and field loss does not happen. Or whatever happens is systematically similar across all wires and all regions in the chip. Is that okay?
So like in the previous example, we were having different kind of spacing in the IO and the array region. So, and why I am calling that structural because I'm able to see the effects of that deterministically, how many variation. But what I'm doing to basically mitigate that if I'm having that?
We add extra metals. So these blue ones are extra metals which are simply added so that density of metals in all regions is similar. This is called as dummy fill process.
So these
You
are
do it in
metals.
the CAD layer itself. Yes, the blue ones are also metals, but they are not connected to any signal. They are floating metals. Now, what does this mean? If you allow this in the memory, what would happen? I said that we do not allow dummy fills inside the memory. Why? What would happen?
Area loss.
Density, area.
Area
No,
loss.
there's no area
No
loss. ये तो
area
जहाँ पे
loss.
layout बना हुआ है उसी के ऊपर ऐड हो रहा है रंजित.
Sir, but
So
wiring.
metal would
Okay.
length would increase if we add them inside the memory, and it can also interfere with the other wires by coupling capacitance.
Yeah, see, you designed your IO region, for example, and you extracted that. You did all your verifications with that IO, is it not? You said, okay, this IO will be repeated 10 times, 20 times, 50 times, depending on number of bits. You estimated the RC of the signal, and then you would do verifications. Then you would characterize setup time, hold time, everything. Now, to add the stage of going on silicon, the system says, oh, there is sparsity of metal 3 there. Let me add dummies of metal 3. So above your IO now, there are dummies of metal 3. What happens? The capacitances of underlying metal 2 would change. The capacitances of other metal 3 lines in that region would also change. So finally, what will be fabricated on silicon will have a very different RC than what you characterized, what you validated, what you designed your circuit with. Can you afford this variation?
So, but I can include this capacitance in my extraction itself. Can't I do that?
So the dummy fill stage is at the fag end. Just before you enter the fab, dummies are filled at that time. Dummies are added to the layout at the last stage, bilkul last stage before fab out, before fab in, let us say.
So, sir, they will be part of my GDS,
but you have not characterized them.
Okay.
They will finally become a part of your GDS. They will finally become a part of your GDS. But when you designed, you did not know that they will come there. So you did not put them. So the capacitances with which you designed were way lesser than what finally are there. Your system will completely go for a toss.
Sir, actually my doubt is having, because once we have done the layout, then we do the parasector extraction, right? And so if we are, and GDS also is a layout file only. So sir, if I've done the layout and at the layout stage I am adding this kind of this dummy fills, then why can't I characterize them?
So as I said, the dummy fills are added at chip level. So you made the layout of a memory. A SOC designer designed the entire chip around it. after everything was done and the chip was being sent for fab out, at that time they felt that, oh, there needs to be 20% more metal 3 so that density is consistent. That is when they added these dummy fills. Now what will you do?
Okay. A SOC level designer is adding this basically. That's why I'm.
Even that designer is not adding, the tool will add.
Yes, sir.
Okay, so you cannot model them. You have to put a layer there which says no dummy, no tiling there, no dummy filling there. Above the memory, you have to put that kind of a layer. Which means there will be some additional DRCs that the memory designer, memory layout designer will have to take care of. We will take care of them, but we cannot accept uncertainty. Okay.
Yes, sir.
So slotting we already discussed earlier, that we make small slots inside wide wires so that there are kind of pillars of silicon dioxide in between, which prevent dishing. Okay.
So one more thing. So signal lines are same as the dummy fill. I mean, the concept is similar.
Signal line is like pre-charge, word line.
Okay. Okay. Oh, yeah.
Signal lines are what you designed.
Okay. Okay. Okay, sir. Got it.
Dummy fills got added later.